Okay, let's talk about time. I mean, we all live in it, right? Our whole lives are measured by it. But when you really stop and try to pin down what it is, it gets slippery.
It really does. People have grappled with it forever.
Yeah.
You know, the idea of a flowing river or Newton's absolute clock ticking away in the background.
Right, and then Einstein comes along and boom, it's a dimension, flexible, part of space-time. Mind-bending stuff.
Absolutely transformative ideas. But what if there's another layer? What if time itself isn't fundamental? What if it emerges?
Exactly. That's the core question we're digging into today. We've been looking into this fascinating concept called the Emergent Time Equation. The idea that time isn't a given, it actually arises from other properties of a system.
That's the heart of it. And our mission here is to really unpack this equation. We want to understand its components, how it works, and what it might imply for all sorts of systems, tiny ones, huge ones. We're drawing on analyses and refinements of this very idea.
Okay, let's dive in. Emergent time. The basic idea, the starting point, is this conceptual equation. T equals C times I0 all divided by E.
T-C-A-I-E. Let's break that down. T is time, but specifically this emergent measure of time we're talking about.
Okay. And C?
C is coherence. Think of it as how ordered or structurally aligned a system is. It's a scale, maybe 0 to 1. 0 is complete chaos, like a jumble of parts. 1 is perfect order, like a perfectly formed crystal.
Order versus messiness. Got it. Then I-arrow. Information density. What's that pack?
Yeah, information density. It's about how much meaningful structure or complexity is packed into a given space or state. Think of a single plain brick versus a really intricate sculpture made of many bricks. The sculpture has way higher information density.
Right. More complex patterns in the same space. Makes sense. And E is just...
Energy. Energy, yeah.
Yeah.
The available energy, the energy flowing through or being used by the system. Energy throughput, essentially.
So T equals order times information divided by energy. What does that actually tell us?
It suggests time pops out of this interplay. More order, more information density that seems to create more potential for time or for complex things to happen over time.
Okay, potential for time, but the energy, E, is on the bottom. So more energy means less time. That feels counterintuitive.
Ah, yeah, that's a really good point to pick up on. It doesn't mean less happens, it means changes happen faster. Think high energy, like a frantic stock market floor versus, say, a slow-growing forest.
Ah, okay.
On the market floor, things change second by second. High energy, rapid change. The internal experience of time within that rapid system might feel compressed, like it's flying by. So this equation is hinting that time is tied to the rate of structural change.
Okay, I see. So it's not just a clock. It's about how fast the system's organization itself is evolving, driven by energy. Now, I remember the sources talk about refining this, especially the energy part.
Yes, exactly. This is where it gets, well, even more interesting, I think. The refinement suggests we can think of energy, E, as the rate at which that information density changes over time.
The rate of change of information.
Mathematically, you'd write it as E equals dI density divided by dt. Energy is the engine driving the system to become more or less complex over time.
So energy is what makes the information patterns shift. Okay, so what happens if you plug that definition of energy back into the original T equals CEIEE equation?
What do you do that substitution, replacing E with dI density dt, and do a bit of mathematical rearrangement, you get a new form. T equals C times dt divided by dln I density.
Whoa, okay. T equals CETTDLN, a density. That looks, well, it looks more complex. What insights does this version give us?
It tells us a couple of really key things. First, time T is still directly tied to coherence. C, more order, more capacity for time. That stays.
Right.
But second, and this is the big shift, time is now inversely related to the rate of change of the logarithm of information density.
The logarithm. Why the logarithm? What does that do?
The logarithm introduces a kind of scaling. It means that if the information density is changing really rapidly, like skyrocketing, the emergent experience of time actually slows down.
So lots of rapid information change equals slower time.
In this model, yes. Conversely, if the information density is changing very slowly, almost static, time speeds up, stretches out.
Yeah.
And if it's completely static, dln I density becomes 0, and mathematically, T approaches infinity.
Infinity. So a system where the information is totally frozen, unchanging, it would be timeless.
Essentially, yes.
Yeah.
Like a perfect crystal, maybe?
Yeah.
From the perspective of this emergent time, it exists outside that flow. No change, infinite time, which is effectively timelessness.
Wow. And the opposite, Wildly fluctuating information.
That implies time compression, a faster internal clock, you could say. This version really paints time not as smooth, but as something pulsing with the information dynamics of the system.
This is definitely leading to some deep questions. The sources get into this paradox, right? What happens when t gets really, really small, near 0, or maybe near 1?
Exactly. These are the boundaries. If t approaches 0, it signifies almost no time passing, a frozen state. Absolute stillness, temporally speaking, no change possible.
A true stop. And t equals 1. That doesn't sound like much time either.
No, it isn't. T1 represents something like time reduced to a single indivisible moment, a snapshot. There's no before or after within that moment, no duration we can perceive, like a single frame of a movie, isolated.
So both ends of the scale seem to point towards a lack of ongoing time as we usually think of it. The sources suggest it's more like a gradient, though.
Precisely. Think of it as a continuous measure. 0 is absolute stillness. As t increases from 0, it reflects an increasing capacity for distinct states to emerge, for change to happen. That value 1 might be a sort of threshold, the minimum chunk of change that constitutes a moment.
And there were other ways to express this idea of time as differentiation.
Yeah, the sources mention a few alternative formulations just to explore the concept.
Yeah.
Like t equals c, d-i-d-e, focusing on coherent change, how information changes relative to energy, weighted by order.
Okay.
Or t equals dsde, linking time to entropy change, ds, relative to energy. Or even tlnii, a logarithmic measure comparing current information I to a baseline, IREI. They all try to capture this idea of time emerging from change.
Now, going back to that first equation, t equals CAIE, you mentioned a potential issue, something our sources flagged.
That's right. The problem is when energy, E, gets very, very low, approaching 0. Mathematically, dividing by 0 is a no-go. It's undefined.
Right. But conceptually, you'd think 0 energy should mean no change, therefore no time. It feels like it should lead to timelessness, not an error.
Exactly the point. 0 energy should intuitively mean t goes towards infinity, representing that timeless state.
Yeah.
So the model needs a slight tweak to handle this.
How do they fix it?
A refined version is proposed. T equals CEAI density divided by E plus A. That little symbol, or epsilon, represents a very, very tiny positive number, something incredibly close to 0, but not actually 0.
Okay. So like a tiny, tiny buffer, just enough energy to keep the math working.
Precisely. It prevents the division by 0 issue while still capturing the core idea. As E gets vanishingly small, E plus A is still positive, but tiny, so T becomes enormous, approaching infinity, which aligns with the idea of near timelessness at near 0 energy.
It keeps the concept intact that time emerges from energy enabling information to change. Okay, that makes sense. But then the sources went even further, exploring different variations of the main equation. Why not just stick with one?
Well, the thinking is that different kinds of systems might experience or manifest time differently. The relationship between coherence, information, energy, and time might not be exactly the same in, say, a biological cell versus a quantum system versus a black hole. So these variations are like different mathematical lenses.
Different tools for different jobs. Okay, let's look at them. Variation 1 was the original, T equals C, A, I-E. We know its strengths and that low energy issue.
Correct. Variation 2 introduces a logarithm. T equals C, Ari, LNIE.
The log, again, what does that do here?
It smooths things out. With the logarithm, time doesn't shoot off to infinity, even if energy gets extremely low, though it still gets very large. This might be more realistic for systems where energy can never truly be absolute 0, where there's always some background fluctuation.
Okay, good for systems with a baseline hum of activity. Variation 3.
That's the square root form, THA. This one's described as being more stable. The square root dampens extreme fluctuations. It makes time less sensitive to sudden huge spikes or drops in C, I, or E.
So a more controlled response.
Exactly. And interestingly, the sources suggest this square root version might be a good candidate for modeling time in biological systems, maybe even related to quantum effects in mitochondria QMT. It balances stability and dynamics.
Biology. Wow. Okay, variation 4.
Variation 4 goes exponential, T equals E, A-E-K-I-E. This is the opposite, extremely sensitive. Small changes in coherence or information density can cause the emergent time value to blow up exponentially.
Whoa, where would that apply?
This suggestion is perhaps in high-coherence quantum systems. Think entanglement or superposition, where tiny shifts can have massive, instantaneous seeming effects. Maybe this captures that rapid temporal expansion.
Quantum time explosion.
Oh, okay.
And the last one, variation 5.
Variation 5 is T equals C, I, I-E-E. It squares the information density term. This makes time incredibly sensitive specifically to changes in information.
Doubling down on information.
Right. The idea is this might be relevant for systems where tiny bits of information have huge consequences.
Yeah.
The classic example given is genetics. A small change in DNA sequence can lead to massive changes in an organism. This equation reflects that high leverage of information.
Okay, 5 different lenses. Original, logarithmic, square root, exponential, and information squared. And the sources then tried to map these onto real-world systems.
Yeah, they explored the potential applications. As we said, maybe the square root for biology, balanced, stable, yet dynamic.
Right.
Maybe the exponential for certain quantum phenomena, capturing that high sensitivity and rapid change. And that information squared one, perhaps for complex information systems like AI, or even trying to model aspects of consciousness, where subtle information processing might dramatically alter the subjective experience of time.
It's pretty amazing to think one core idea could branch out like that, from cells to AI. What about the really big picture, cosmic time?
The sources touch on that too. On a cosmic scale, emergent time could be seen as tracking the unfolding of structure galaxies forming, stars burning, driven by energy interacting with matter and information across the universe.
So the universe itself has an emergent time based on its overall C, I, and E.
That's the implication. And it leads to fascinating thoughts about extremes. Black holes, for instance. Maybe they represent infinite information density, or a breakdown of coherence, leading to a region where time, in this emergent sense, behaves very differently, perhaps approaching timelessness again.
And stars.
Stars are high energy, high structure, maybe high coherence in their own way. Perhaps they experience a faster form of emergent time compared to the cold void of space.
This feels fundamentally different from how Einstein described time. The sources made a point of comparing them, right?
Yes, it's a crucial contrast. Einstein's relativity shows time isn't fixed. It's relative to your speed and the gravity around you. Time dilation is real.
We measure that.
Exactly. Emergent time is suggesting something else, or perhaps something complementary. It says time also arises from the internal state of a system. Its order, C, its information, I, and its energy, E. Higher C and I tend to stretch time out. Lower E leads towards timelessness.
So Einstein is about external factors, gravity, velocity. Emergent time is about internal factors, structure, information, energy.
That's a good way to put it. It's looking at time's origin from a different perspective, focusing on information dynamics and thermodynamics within the system itself. Maybe it's a generalization or something that becomes more apparent in certain scales or in information-dominated systems.
It really reframes things, and this even extends to the idea of, well, nothingness itself.
That's one of the most profound implications, I think. If time emerges from C, I, and D, then what is true nothingness? It would have to be a state with zero coherence, zero information density, and zero energy.
Utterly empty and disordered.
And therefore, inherently timeless. A state without change because the ingredients for emergent time simply aren't there.
So existence itself, the universe, life, it's all the process of C, I, and E emerging from that potential nothingness. And time is the measure of that very emergence, that unfolding.
Beautifully put. Time isn't just the container, it is the unfolding. It's a dynamic expression of reality becoming structured and complex, powered by energy.
Wow. Okay. This has been a lot to wrap my head around, but incredibly fascinating. As we finish up this deep dive, what's the main takeaway you want people to hold on to?
I think the core idea is just to entertain the possibility that time, this thing that feels so constant and fundamental, might actually be an emergent property, that it's deeply interwoven with the structure, the information, and the energy of everything around us and within us.
It really shifts your perspective. If time isn't just the background clock, but arises from how things are organized and energized, what does that mean for aging, for consciousness, for the beginning and end of the universe? It makes you wonder, doesn't it?
Absolutely. It invites us to think differently. Maybe look into information theory, thermodynamics, cosmology with this lens. What if time isn't just happening to us, but is an expression of reality itself? That's the thought I'd leave everyone with.